Bismillahirrahmanirrahim. We are studying chapter 5, brake system. Today is the fourth part or the final part of our chapter 5, brake system. First, a quick recap. In first part, we have covered the basic definition of a brake and the function of a brake, the block diagram of a brake, then the parts or sub-assemblies of the brake, drum brake and disc brake. And typical brake system components, the types of brake, the drum brake and disc brake. I've uploaded a few video clips for your better understanding, then the brake design requirement, and then brake system categories, and few words regarding the drum brake advantages and disadvantages, then parts, then non-servo brake design, and brake hydraulic system. This was the hydraulic master brake master cylinder or hydraulic master cylinder of the brake, its complete function, how the valves operate, how the piston operates, and how the pressure is maintained there. Then in second part, we have discussed in detail the brake master cylinders and its brake proportioning valves, what the proportioning valve do, the reason and purpose for that, and what is the slip point and the slope do. And then we discussed electronic brake proportioning. Then we talked about metering valve or hold of operation, purpose and function of the metering valve, system without the metering valve, diagonal split, and front wheel and rear wheel brakes, then combination valve. Then we talked about the brake fluid and the rubber parts which are present in the brake system. This was our second part of the brake chapter lecture. Then the third part, we have talked about the anti-lock braking system. We talk about what is the anti-lock brake system and what is vehicle with conventional braking system and anti-lock braking system. And then we have seen the different factors which are affecting traction, the skid factor, and all these things. Then the tire slip and the braking distance on different parts. Then the expert driver versus the ABS braking system. Then the limitation of the braking system, and then ABS components and operations. Four major parts of the ABS components, then wheel speed sensor is input, then the controls or solenoid valves, then the systems configuration, the 4-channel system, 3-channel system, single channel system, and integral and non-integral configurations. So ABS operation in schematic view, then anti-lock braking system in a vehicle, how it's looked like in non-integral type. And then we have a schematic drawing of a typical anti-lock braking system. This was part 3. Now today's part is chapter of brake system, the 5th chapter and the last part regarding the brake performance. And this part or this portion of this chapter I will be covering from this second book, The Fundamental of Vehicle Dynamics by Thomas D. Gillespie. In this part, we will be covering about the dynamics of the vehicle and how the brakes factors or brake forces are acting on that. In order to understand the dynamics of the vehicle and the brakes, first let's define the vehicle fixed coordinate system. The fixed coordinate system. Now let's see, this is your CG of the vehicle, center of gravity, and vehicle is moving in this direction, X direction, and this is the longitudinal direction. So X direction, we have a longitudinal direction X, and on the right side we have Y direction, the lateral direction, and on vertical side, on going downward, is your Z direction, the vertical direction. So along the longitudinal direction, we have roll P. On the lateral direction, we have a pitch Q. And in vertical direction, we have a yaw R. So these are the vehicle fixed coordinate system. Now on board, the vehicle motions are defined with reference to a right-hand orthogonal coordinate system. Simple, in our childhood, we know the right-hand rule. So we will apply the same right-hand rule. The On board, the vehicle motions are defined with reference to right-hand orthogonal coordinate system, the vehicle fixed coordinate system, which originates at the center of gravity and travels with the vehicle. By Society of Automotive Engineering convention, the coordinates are x, this one, forward and on the longitudinal plane of the symmetry in x direction. Now, y, lateral out the right side of the vehicle. This is the lateral outside right side of the vehicle. Z, this one, downward with respect to the vehicle. Now P, roll, velocity about the x-axis. So P is the roll velocity about the x-axis, and Q is the pitch velocity about the y-axis, and R is the yaw velocity about the z-axis. So this was the vehicle fixed coordinate system. Now let's talk about the Earth fixed coordinate system. This was according to the vehicle fixed coordinate system. Now on the surface which vehicle is moving, it has its own fixed coordinate system, the Earth fixed coordinate system. Let's see we have this XY plane in which our vehicle is moving. X is the forward travel, the projected one, this one. X is the projected forward travel, and the projection of instantaneous velocity is in this direction, but we are making a turn here. So this is the vehicle path. So projection of instantaneous velocity is in this direction, X projection is in this direction, and the vehicle path is in this direction while we are turning. So y, travel to the right. So right hand rule, travel to the right. X is in the forward direction. Z is the vertical travel positive downward. So Z is the vertical travel positive downward. And this psi, heading angle between X and X in the X ground plane. So the projected X direction, and with the x-axis, the angle which is make heading angle, that is your psi. Nu, the course angle, the angle between the vehicle velocity vector and x-axis. So this is the projection of instantaneous velocity. So the angle making with the x-axis is the course angle, and this is positive. This heading angle is the projected one, and this is the projection of instantaneous velocity. And beta, the side slip steering angle, the side slip angle beta, angle between the x-axis and the velocity vector. So this is your slip angle, negative angle shown. So these are the Earth fixed coordinates. Now let's see the basic thing. You have a vehicle moving on a hillside, okay? So that is making a theta degree angle on this inclination. So let's see the forces which are acting on. So starting from the front, dA is your aerodynamic drag force, which we are acting because we are moving in this direction. So HA is the height of the aerodynamic force, on which height the forces are acting. Now W over G, as we say, weight over or gravity, is the mass. AX is the acceleration in X direction. So this is your point center of gravity. So we have divided the weight into sine factor and the cos factor. So W is W sine theta, W cos theta along the x-axis, along the y-axis. So weight is in this vertical direction. So height, on which from ground to the center of gravity point. Now DH is the distance from the axle to the hitch point. RH and RX are the hitch forces in Z direction and X direction, and HH is the height of the hitch. RXL is the rolling resistance front rolling resistance rear, and the Fxf and Fxr are the forces in the x direction of the front and the rear, and this is the front wheel weight or front axle weights, and this is the rear axle weight. So distance from the front axle weight to the center of gravity is now denoted by beta b, and distance from the center of gravity to the rear axle weight is c, and the total b plus c, the total distance from the front axle to the rear axle, is denoted by L, or L is equal to b plus c. So we have covered all the forces which are acting. So now let's see. The general equation for braking performance may be obtained from Newton's second law written for x direction shown in this figure. So F, we know it's simple from the Newton's law, second law of motion. F is equal to ma, and m is the mass of that vehicle. Ax is the acceleration in the x direction. So in terms of this figure, this will be minus weight of the vehicle divided by the gravity into dx. Dx is the equal to minus ax linear deceleration, where w is the weight of the vehicle, g is the gravitational acceleration, dx is equal to minus ax, the linear deceleration, Fxf is the front axle braking force, Fxr is the rear axle braking force, d is the aerodynamic drag, and theta is the uphill grade, the angle which is making from the ground. So F is equal to ma, and in x direction, F is equal to max, linear deceleration. So minus w over g into dx is equal to minus front axle braking force minus rear axle braking force minus aerodynamic drag forces, and minus weight into sine theta, the in x direction. So this will be the basic equation for attributive forces acting on a vehicle. Now, the energy and or power absorbed by the brake system can be substantial during a typical maximum effort. The energy absorbed in Now, assuming forces acting on a vehicle will be constant throughout a brake application, so F is equal to ma, we know the A is equal to dx. So F forces Fxt, the total of all the longitudinal deceleration forces on the vehicle, we take it as positive. So all the longitudinal deceleration forces divided by the mass is the dx, the linear deceleration. So we can say that it is minus dv over dt, derivative of velocity divided by derivative of time. So v is the forward velocity. Now, integrate this equation from initial velocity to the final velocity into derivative of v is equal to minus fxt over m, the total of all the longitudinal forces, deceleration forces divided by m, from 0 to interval to time ts, time for the velocity change, into derivative of time. So after doing the mathematical functions, we got initial velocity minus final velocity is equal to fxt divided by m into t of ts, the time for velocity change. Now, assuming force acting on the vehicle will be constant throughout a brake application, so V is equal to dx over dt, because we are assuming that it is constant throughout the brake application. So we can substitute dt in equation 3.2, integrating and obtaining the relationship velocity. And so initial velocity square minus final velocity square divided by 2 is equal to fxt divided by m into x. X is the distance traveled during the deceleration. So in case where the deceleration is full stop, then final velocity is 0 and x is the stopping distance. Then stopping distance is equal to v initial square divided by 2fxtm. So we can write that the stopping distance is equal to v initial square divided by 2 into dx, the linear deceleration. And the time to stop this is Ts is equal to V initial velocity divided by Fxt divided by m. So we can write that T time to stop is equal to initial velocity divided by deceleration. So the energy and or power absorbed by a brake system can be substantial during a typical maximum effort stop. The energy absorbed is the kinetic energy of the motion for the vehicle and thus dependent on the masses. So energy is equal to half mv square. So half mass divided by 2 initial velocity square minus final velocity square. Over the entire stop, the average power absorbed will be the energy divided by the time to stop. So we can write the power equation. Power is equal to half mv square divided by the time. So this time factor, when we divided this energy by time, it comes to the power. So final velocity is when a vehicle is deadly stopped. So final velocity will be 0. So it's initial velocity squared divided by the time to stop. Now the braking forces, the forces on a vehicle producing a given braking deceleration may arise from a number of sources, which are: first one is the rolling resistance, very important. Rolling resistance always opposes vehicle's motion, hence it aids the brakes. The rolling resistance forces will be, we can write that rolling resistance front plus rolling resistance rear is equal to rolling resistance coefficient, the FR, into front weight, front axle weight plus rear axle weight is equal to rolling resistance coefficient into the total weight of the vehicle or the rear and the front axle weight. Second is the aerodynamic drag the braking force depends upon. The drag from the air resistance depends on the dynamic pressure and is thus proportional to the square of the speed. So the drag from the air resistance depends on the dynamic pressure and is thus proportional to the square of the speed. At low speed, it is negligible. At normal highway speed, it may contribute a force equivalent to about 0.03 gravitational force g 1 foot per second square. Now, the third is the driveline drag. The inertia of these components adds to the effective mass of the vehicle and warrants consideration in brake sizing on the drive wheels. Engine braking disappears when an engine over-reverses excessively and result in a valve floating. On manual transmission with clutch engaged during braking, the engine braking is multiplied by the gear ratio selected. In automatic transmission, engine drags does not contribute substantially to braking on the vehicle so equipped. Whether or not driveline drag adds in braking depends on the rate of the deceleration. So it depends upon the driveline drag depends on the rate of the deceleration. Now braking force, fourth is the grade, the angle. The road grade will contribute directly to the braking effort, either in a positive sense uphill or negative downhill. Grade is defined as the rise over the run, vertical over horizontal distance. The additional force on the vehicle arising from the grade Rg is given by the grade resistance or the road grade is equal to weight into sine theta. For small angles, typically of most grade, theta radians is equal approximately grade rise oblique run. So Rg is equal to W sine theta is approximately W theta. Thus, a grade of 4%, 0.004 will be equivalent to deceleration of plus minus 0.04 g, so 1.3 feet per second square. Now the brake factors, which are the brake factor is the Mechanical advantages that can be utilized in drum brake to minimize the actuation effort required. As we know from the first part, the drum brakes require less force or pressure as compared to the disc brake to hold up. So the brake factor is a mechanical advantage that can be utilized in drum brakes to minimize the actuation effort required. So let's see the drum brake, this figure. The drum is rotating in a clockwise direction. It is pivoted, the drum brakes are pivoted at these 2 points, and here we have the wheel cylinder. Okay, so this is the first leading edge, and this is the trailing edge. So leading shoe and trailing shoe. This is the lining material which is in contact with the drum. So E is the perpendicular distance from actuation force to the pivot point. Here, if you remember, we have a wheel cylinder from where when we apply a brake, the hydraulic pressure comes in and the pistons move outward. And when the piston moves outward, right and left, the brake drum brakes try to contact with this drum. So these parts move in opposite direction, but here it is pivoted. So this moment, this distance, perpendicular distance from the actuation point, actuation force to the pivot, this is known as E, and A is the normal force between the lining A and the drum. So this is the normal force between the lining A and the drum. And this one, from pivot point to this point of contact, the lining force, the perpendicular distance from lining friction force to the pivot, and M is the from perpendicular distance from the normal force to the pivot in this direction. So taking moments about the pivot point for a shoe A, this one at this pivot point, summation of moments at B is equal to EPA plus N nu N A minus M and A is equal to 0. The friction forces developed by each brake shoe is FA is equal to nu N A, and FB, the leading and the trailing, is nu N B. Then equation 3-15, we can write F is equal to MA. Force is equal to pressure per unit area. FA divided by PA is equal to nu E M minus nu N, and FB over PA is equal to nu E M plus nu N. So with this, we comes to the end of chapter 5, that is the break. So thank you very much.